All right, so what we'll do today, I want to do problems 1 and 4. 1 and 4, and then I want you to do 2 and 3 on your own. Now, when you get done, remember, we've done 2 worksheets. One I have not checked from Friday, so goal will be to show me both of those to get credit. And then what we'll do from here is this. Don't forget about the homework and the chapter 17 test, which will be on Friday. Any questions before we get going? Correct. Yeah. All right, so here we go on this. So instantaneous rates. An instantaneous rate is saying, hey, what is the rate at this specific moment? Typically, you are given the rate law. In this case, we're given the rate to be equal to K times the concentration of A times the concentration of B squared. So all we have to do is this. Because we are given the values and we're given that K and also the rate law, we can go ahead and plug this into our equation. So we're going to start out and we're going to say rate equals, and instead of putting K, we're actually going to put the value of K, which is listed at 4.75 times 10 to the negative 7. So we have 4.75 times 10 to the negative 7. And that has the unit, in this case, of n to the minus 2, s to the minus 1. Now, because it's in scientific notation, I like to put this stuff in parentheses. We then multiply it by the concentration of substance A. So we're going to say times 0.355, and we raise it to the first power, and we say times our concentration of B, which is 0.0122. Now, the unique thing about B, in the rate law, it says, hey, we have to square it. So when we calculate this, 2 things to be aware of. Number 1, we have scientific notation with our K. Number 2, don't forget to square this. So how I type this into the calculator is parenthesis 4.75 times 10 to the negative 7. Close the parenthesis times 0.355 times parenthesis 0.0122 squared, and then I close the parenthesis. I realize that I write it outside, but to make sure that it squares the right value, I put it inside the parenthesis on my calculator. So if I press enter, I get a rate of 2.51 times 10 to the negative 11. Now, the question I have for you, our K has this unit S for seconds. So what would be our unit for rate in this case?
M/S.
There we go. M/S would be our rate. Now, on number 2, it's essentially 2 different problems. One thing that's been confusing up to this point is that it says rate equals K, and then it gives you that substance, and it's to the first power there. What's confusing is this. I give you the temperature in Kelvin. So on the bottom part of number 2, you have 1,273 Kelvin. Cross that out because that's important, but it doesn't help you calculate it. Your K value, your rate constant for number 2, is 87. Now you're going to view these as 2 different problems. Problem A says we have a concentration of 0.01. You're going to find the rate, and then you're going to say, what is the rate of problem B, which says what is the concentration of 0.2. Questions?
So we're doing the same thing, but like only for A and only for B.
And number two, I actually give you the substance. I can work with you. Once I walk through it, it'll make more sense. All right, any other questions before we move on to number 4? Okay, with number 4, the first thing I want you to do is this. When I typed this out, I made a mistake of balancing. And down here on this second bottom equation, I had 2H2O2. It should not be 2H2O2. It should just be a single H2O2 here on the bottom. So just cross out that 2, and that's going to help us balance this. Okay. Now, we go through this and we want to find the overall reaction. We want to write the rate law, and we want to draw that reaction diagram. So first things first, we want to add these things together. Now, before we add the things together, we can cross out, we can cancel some items. There are actually 2 items we can cancel out. Somebody yell out 1, or we can cancel these things before we add them together. Okay, IO negative. Now, IO negative is produced in one step and consumed in a later step. In fact, the next step. We call those things, started with an I.
Intermediate.
There we go, intermediate. Yep. Now, there's one more substance that we can cross out before we add them.
I negative.
There we go. Now, this is new. We did not see this in our example problem from notes. I negative can cross out or cancel out. This is because I negative is considered our catalyst. And the reason it's considered a catalyst and not an intermediate, we start with it as a reactant in one step, and then later, in a future step, we produce it as a product. That's the difference between an intermediate and a catalyst. Now, we've crossed out everything. We can add this equation together. So on the left side, in fact, the only thing we have is H2O2 plus an additional H2O2. So how many do we have? Good, 2 H2O2. And like I said, that's the only thing that we have on our left-hand side. On the right-hand side, I'm going to start out, I have H2O plus H2O. So how many? 2 H2O. And then it has 1 oxygen. So we say plus O2. Now, this thing right here is considered our overall chemical reaction. And I realize really all we've done is add these things together. Typically what we want to do is, remember, these are like mini steps that get to the entire overall reaction. Sometimes those mini steps don't add together, okay? So this is kind of a check. Hey, yeah, this is what we actually want. Cool. If that works out, we can keep driving on to going through our proposed rate law. Now, next step is figure out the rate law. The rate law is determined by the rate determining step, which in these 2 equations, we have a slow and fast reaction. Which equation would be the rate determining step?
The slow one.
Very good. Slows it down. Think of it as stoplights, okay? There's 2 stoplights. We get stopped at the first. That is going to slow us down, and so that's where we get our rate law. Now, in a rate law, our rate equals K. We can guarantee that is going to occur. With our rate law and with our slow reaction, we are only concerned about our substances in our slow reaction. And we're only concerned about reactants. So in that slow reaction, I'm going to block out everything that's a product. And I'm going to ask you this. We're going to put H2O2. We're going to put H2O2 as a substance in brackets. And then we have to look to our equation and we see what coefficient is just in front of the H2O2 in our slow equation. 1, so we'd raise that to the power of 1. And then this is kind of weird. We don't normally see a catalyst in the stuff that we do. Remember yesterday when I said, hey, this isn't included in the rate law? Well, that was because we already added it together. So this is like step 1. We haven't crossed it out. So technically, we would have to include I minus into our rate law. Okay? This is kind of a unique circumstance here. What we need to recognize, slow reaction, that's where we're going to write our rate law in this series of steps in a reaction mechanism. Now, our last thing is this, our reaction diagram. So we have a chart that looks like this. We have on the x-axis the reaction progress, and then on the y-axis, the uppy-downy one. Yep. And I didn't really talk about this a whole lot in notes, but I'll talk about it now. We have to factor when we draw our lines and our hills, is it endo or exothermic? It's really easy to put on the graph. It is exothermic, which we'll talk about here in a second, but we're going to have 2 hills. Which hill or which reaction is the highest hill?
Slow.
The slow reaction. So we're going to start out and we're going to draw a giant hill. And it's going to come up. That's reaction number 1, the slow one. We'll go through a little baby hill. And then what I'm going to do is I'm going to really emphasize down here, our products are lower than energy than our reactants. And so that means we have an exothermic reaction. If it was endothermic, your reactants would be lower in energy than your products. Questions? Okay. Knock out the rest of this worksheet, show me, and then also the worksheet from Friday as well.